Hello, everybody. I'm Pete Meyer, standing in for Jason Key. The observant of you will notice I don't sound like Jason. So today we have a webinar by Nigel Moriarty, and thank you for joining us, Nigel. One other note to mention, if you are on a Mac and you have heard that 10.15 Catalina has come out, we recommend you not upgrade to it because we're still testing all of the things that will possibly break on the SBGrid side. And with that, I will turn it over to Nigel. And Nigel, thank you for presenting today.
So thank you very much. And I guess that even though the technical difficulties were there, we were going well. So the systems check, we just skip over this, do we?
Yep. We have checked the systems, and the systems are now working. Thanks for your efforts. So.
No problem. So just for some information, Amber and in Phoenix is currently available, and I should tell you that Phoenix is a collaboration between 4 major groups. There's the Paul Adams group at Berkeley, of which I am a member, and you can see my information on the bottom right side there. We also collaborate with Randy Reed at Cambridge University in Cambridgeshire, and Jane and Dave Richardson, who provide more probity and validation support, and Tom Terwilliger, who is pushing forward with a big effort to do cryo-EM. If you're interested in Phoenix, we have a feature article in this month's Crystal Act D, and I show you the cover just because we're very happy to on the cover, and then you can take a look at this citation as shown. The information in this talk, however, is on bioRxiv. It's a preprint of the article that we're working on. Sorry, and you'll notice that there is some of the people I've already mentioned. You can see there's the DOI there. Jane is involved, and you'll see her work a little bit later. Dave Case, who is one of the gurus of Amber, was also involved, as well as you can see, 3 other people from his group. So it was a real collaboration, and we're very happy that both Phoenix and Amber were working together on this project. So the headlines can be taken in 3 major points. If you use the Amber force fields gradients, you get improvement in the major validation metrics, and I will show you that a little bit later. And this is especially true at low resolution, where the experimental data is not enough to do ideal geometry. C-beta deviations, on the other hand, are usually larger when you're doing Amber, and that headline is a little bit of a teaser because it's not clear why that would be the case. You would think that all validation metrics would go in the same direction, and this teaser will be answered later as well. An aside is that bond and angle RMSDs are higher, but this has limited meaning because the RMSDs are calculated between the resulting values in the geometry compared to the ideal values of the conformation-dependent library and Eng and Hoover. So these are the standard ideal values that are used in standard refinement, and the Amber values are different. And so the RMSDs are different. If you're asking why don't we just calculate an RMSD to the ideal values of a force field, that is not a concept that force fields have. And they don't try and force the geometry to an ideal. They try and push the gradients in the direction of better chemistry. And I can talk to people who want to know more about that. So We did an experiment. Obviously, when you create a new program, you want to do an experiment. So we did it on the whole protein data bank, and we filtered the data bank based on the experimental data. So we didn't want to do it on everything. So we excluded twinning, made sure that the data was 90% complete, and we made sure the R values were not in a bad range. We also filtered on class score, and the reason for that is that especially at low resolution, if a region of the model is in a very bad minima and not close to the real minima, class score will go through the roof, and there's no way that a refinement is going to take it from that bad minima to the correct one. So class score is an indication of inconsolable differences. I'm going to put it that way. This model is never going to get better without doing a lot of manual rebuilding. And we limited it to resolutions better than 3.5. We did do some testing out to 4, and the trends continue. So we also excluded some things from the model as well. So we did not have any models with RNA or DNA, that did not have any models containing ligands with metals or metal clusters. And this is based on the limitations of AmberPrep, which I'll talk about later, and the covalently bound ligands. The problem with covalently bound ligands is that the force field parameterization has to change for both the ligand and the protein entity that it's attached to. So that is currently not available. And the reason why RNA and DNA were excluded is because of the high charge and the need for some specialized charge shielding, etc., that has not been automated. So with that, I have already mentioned AmberPrep, and this is a tool that we created to facilitate this process. So it takes an input file, and in this case, it's a PDB model file. So if you have a model and you run Amber, Amber refinement, you have to do this. It creates a model file for Phenix. Now, this is by default named for Phenix, and this model contains the atoms in the order that the other files further down requires. And Amber has some nuances that it likes to receive certain atoms in certain orders and whatnot. So this was a requirement. There are 3 files that Amber uses. We are hoping to reduce that too. But you can see the first one is RST7. This is a coordinate file, and it is a format that the Amber modules require. The second file is the parameter files. So this has the information of the force fields for each atom in the model. And then the order file is actually it's a Python mapping between the order of the atoms in Phenix and the order of the atoms in. So we're hoping that the RST7 file will go away, and you'll only have to keep track of 2. So some of the internals of AmberPrep. This is actually a very interesting story, because before we could write this, we had to figure out that both suites of tools needed to be used. So AmberPrep uses some of the tools in Amber Tools, which is a open source, open license part of Amber to create the force field files. It does use Elbow, which is a tool in Phenix that is designed to create ligand files for restraints, but it also knows how to protonate these ligands, and it can provide the correct protonation, which is required to create the correct parameterization of these ligands. So then these ligands use some of the Amber tools to get a semi-empirical quantum mechanical minimized geometry so that you can get the best parameters possible. And it also uses Molprobity's reduce to add hydrogens to the model, because that is required for the correct parameterization as well. As I recall, Amber Tools did have its own implementation of reduce, but we're also now. So both the packages were needed to help get close to automation. Continuing with the experiment.
Need the microphone and still hear it.
Continuing with the experiment, I'm listing the unusual, by that I mean the non-default I used experiment, and you can see first one is the C beta restraints has been set to false. So this means that because by default in an ordinary refinement, the standard refinement, C beta restraints are placed on the C beta atom to keep it in the correct position. That was, if we had that on true, it would have been an unfair comparison, as you'll see later. We also did not restrain the psi and phi. The strategy is the steps that are taken by a refinement. And the only thing that I changed is this bolded option. It's called individual sites real space. So during a refinement, by default, at each macrocycle, once a reciprocal space refinement has been performed, there is a real space refinement is performed as well to see if a real space refinement will improve some of the features and the fit of the model. If it doesn't, it is discarded and it moves forward. But because Amber wasn't playing a role in the gradients for the real space refinement, off. That doesn't mean that you don't have to turn it off. It just means that there will be a duality in your refinement. The fourth option, flip symmetric amino acids, equals true. That there are some amino acid side chains that are symmetric, like arginine is the biggest example, I guess, and the nitrogen atom in the guanidinium group, the two at the end are symmetrically similar, but it's best for the IUPAC standard if the NH1 is in the cis formation. So I usually do that because I think it's a good idea. The last two options, the optimize XYZ weight is true. This, by default, it's false because Phenix has a lookup table where, based on features of the model and features of the data, it makes a guess of the weight and then optimizes it macrocycle afterwards. However, if you want to be more proactive and get a better optimization, I guess, for the weight, this option at each macrocycle will run 10 refinements with different weights, which is the best one. We did this to see if this would help with the Amber refinements, and it certainly does. The other thing we did was make sure that the macrocycles were larger than the default of 3, so that we could get much closer to convergence. And this is particularly true for two reasons. One, if the R3 flags were not in the download from the PDB, you need to optimize to convergence there. And we also wanted to make sure that if for some reason the AMBER geometry was being pushed in a very different direction, we wanted to make sure that it reached convergence as well. And there is some evidence that have to do a few more steps if you start with an AMBER refinement so that you can approach convergence. So users should keep an eye on that to make sure that they have done so. So there obviously are some results. We did actually manage to get nearly 24,000 pairs of refined models that fit the criteria that specified earlier. This is quite a large number because of even the restrictions for AmberPrep. You would think it would be a lot smaller. And then in the usual way, we compared the results using mold probity and all of the different metrics on probity. The distribution of the histogram for each resolution is shown here. At 0.05 angstrom, at 0.5, there's still about 80 refinements in that bin, and so there's quite a good representation across the board here. We chopped it for presentation purposes at resolution of 3.2 because it gets quite small further out, and I wanted to have reliable statistics. So here's the meat of the talk, in that just about everything is better with AMBER. The blue standard Phoenix refinement and the burnt orange represents the AMBER results. The overall mold probity score, as you can see, is quite similar at high resolution, I should say, and then at low resolution, out at approximately 3, the difference in the mold probity score is between 2 and 2.5. The error bars here stand for the standard error of the mean, and I also have done box plots using standard deviation and everything, and still going compelling argument that AMBER is doing a better job. It's more marked, as you can see, in the class score. The class score is halved approximately out at 3 angstrom resolution, and even at 2 and 1.5, there is some slight improvement. The same goes for Ramachandran. The favoured is slightly better, and the outliers are slightly less. Those outliers is a very small number there, so not going to be something that wouldn't be the reason to do AMBER. The rotamers are very, very similar, so there's nothing going wrong there. And then the hydrogen bonding is greatly increased when you use AMBER compared to the standard. And this is true, once again, at low resolution compared to high. So that's all very impressive. We're happy, but when it came time to look at CBD deviations, there was a very different story. Now, this is a plot of the percentage of CBD deviation. So it's the percentage of C beta atoms that are outside the desired radius. So that's 0.25 angstrom, as determined by the algorithm that was developed by the Richardsons. And you can see that a standard refinement using the CDL and Angenhoover, it's almost 0 at resolutions worse than 2 for sure. And so that is pointing to the fact that the restraints standard deviation are very much pushing the geometry in that direction. However, the C beta deviation in amber is always larger. So at high res, instead of being 0.02%, it's 0.04%. Sorry, again, I'm putting the 0 in the wrong place there. It's 0.2 and 0.4%, and these are small values, but they're quite different. And at low resolution, increases to almost 1% of C betas deviation territory. So why is this the case? And that is what Jane was looking at. You can see that overall, a refinement. This is in this example is 3G8L. Half resolution solution. It's got some problems. You do a CDL refinement, things are improved. Phenix does a good job of that now with its different algorithms to try and improve the geometry. But you can also see that Amber does a better job. It has reduced the number of red areas probe map significantly. So getting back to the behavior of the C beta, you can see from this figure there is 4 regimes of resolution, starting at high resolution at the left, and these are reasons why we see C beta deviation. Figure A, it's sometimes the alternative states have been truncated and been put in completely. Sometimes a rotamer is fit backwards. This happens a lot at 1.7 and in that area. Sometimes there is a wrong rotamer is fit and the algorithm can't find correct rotamer, probably because some of the density is missing. And then at 3.5 area, because the density has less features, side chains will be shoved into the density and pushed direction, and that means that you're likely to see a C beta deviation. Now, the point here is that often in the just using CDL and Angular, the C beta is forced to go into the ideal region. Even if you haven't got a C beta restraint applied, the other restraints in the model are such that it pushes the C beta into the region quite strongly. And if you run an Amber refinement, the model is not designed to explicitly put the C beta into the right place, and it shows a deviation in these places like these examples, and you can then actually see there is a problem if you go and have a look at C beta deviation in an Amber refinement. So what we're saying is that in a standard refinement, the restraints will sometimes hide a problem because they're forcing beta into the right place, and sometimes the other evidence not as well defined, and it's much more difficult to find areas that could be problem areas. However, if you do an Amber refinement and look at every C beta deviation, you will in fact see some areas that need tension. And there will be at least one of these four, and there can be other problems as well. So at this point, I'm going to demonstrate how to run Amber. Currently, there is no GUI for AmberPrep. So that means that I'm going to have to use a command line. I hope that doesn't put anybody off, but in some regards, it's probably a little bit of a good thing to have a hurdle like this, because force fields are not plug and play, unfortunately. You do have to be aware of a lot of different nuances in force fields that I've hinted at, like if you change the protonation, you need to change the force field. If you change the bonding, like ligands covalently bound, you need to change the force field. So not a terrible thing. Having said that, we are trying to improve AmberPrep, and there will be GUI. So let me begin the demonstration by downloading a file. I'm going to download 1A0B PDB, and I'm also going to get the data file as well. And so now we have the files. I'm going to now run AmberPrep, and it's very simple. Obviously, I've chosen a file that works, but you'll see that when it does work, it's very simple. Doesn't work, the printout tries to tell you how to solve your problem. So it's going through the steps. This is not a small model. It has a few chains, but now we are done. See that there are the four files that I alluded to. There's the four phenix.pdb, and then there's 4 Amber files that have been named like that to give you a heads up on exactly what to do. And helpfully, we've also put in a command line here that you can paste, like so. And just need to provide it with the MTZ file. So and refinement. And after that, it's essentially exactly the same idea. You're running a refinement, but instead of using gradients from the restraints model that commonly used, it uses the gradients that are provided by Amber. If I've done a refinement before, you'll know that you'll have to do some validation, and you compare it to how things are going with your other refinements. Once this is all in the GUI, it will be much easier, but you can also use the GUI to validate the output from this in a very simple fashion. Shouldn't take too much longer here to do this refinement, but I will show you how to do a complete validation so that you can include this in your GUI processing if that's what you want. So demonstration is really just a way of showing that you can do it quite simply, and that get to the command line, then do it. But as I said, in a little while, this will all be much more automated in GUI. So if you start your GUI, you can see usual stuff. I'm going to show you how to validate comprehensive validation. Browse. This is the output here. Refinement. And selection file. Run. Run. Now, this validation step will be in your history so that you can keep track of project. But like I said, this is only until GUI is complete for AmberPrep and for running Phenix-Refine with Amber. So, and as you can see from here on, it's the same. You can see that our factors are there, and you can go through all of the validation. Okay, so going back to our slides, the conclusions, this is an ideal thing to do towards the end of your refinement pipeline, because, as I said, if you change your model, you have to change your parameter file. So I would stick to doing this towards the end of your refinement. I would definitely recommend it for lower resolution models so that you can improve your geometry, but also highlight areas of concern because of the CB to deviation. These are, I guess, the canary in the mine. It's a way of thinking of it. If you have CB to deviations, you need to go and look at them and try and see if there are other things that are causing this problem. And then do some manual rebuilding and perhaps go through the cycle again. I've already mentioned that we're going to improve AmberPrep. One of those things is to create a GUI for it, but we are trying to make sure that there's more smarts going into it, because there's a few things that could be improved. We're also trying to make it easier for the user to add ligands, and that is another project pipeline. Also, we're going to add it to other refinement programs in Phenix, including real space refinement and ensemble refinement, so you can different, more chemically meaningful ensembles when you ensemble. So with that, thank you very much.
Jason, do you have anything?
Yeah, well, I had a question. I was looking for the statistics you showed were mostly X-ray, and I know a lot of people are working with, sort of, I guess what we call low resolution data in the X-ray world, this sort of 3 angstrom, what do you, the Amber contribution to the real space refinement, is it sort of similar to what we're seeing with the, because here everything gets better, right? So like, that's great, and I think that people in real space refinement are really struggling in these areas.
So that is exactly why the next point of order is to add it to real space refinement. I actually, as a technical issue, it was written a couple of years ago, and it was integrated into the Phenix program package in a very ad hoc manner, the Amber part. And so we are currently modularizing it in a much more Python class or object-oriented way, so that we can plug it into everything. So once I've retrofitted this code to be actually exactly object-oriented, we are going to stick it straight into real space refine and ensemble refinement. Both of those are areas that we feel are very important. And yeah, that's top of my list of things to do at the moment. Great,
thank you.
Yeah, we're very excited about the real space area because it's coming along so well, and we believe that, you know, between 2.5 and 4.5, it should have a good impact. And I don't know if you are familiar with ensemble refinement, but currently ensemble refinement puts out too many non-meaningful geometries because the CDL and Eng and Hubert just aren't able to generate those sorts of things from you know, an ensemble. So we're hoping that Amber will do a much more meaningful job.
So we have 2 questions in the chat so far. Daniel asked, are disulfide bonds reduced during hydrogen addition for input preparation?
Did you say produced?
Reduced.
Reduced. By that, no. I believe the answer is no. They do not have hydrogen on them by AmberPrep.
Okay. And we have another question from Jonathan in the chat. You'd mentioned including or excluding metals at the beginning. Could you comment on the capabilities of including metals? For example, how difficult are things like Mg2+ or zinc and zinc finger proteins?
I should be clear, single metals are perfectly fine. So yeah, Mg2+ and zinc are all there. All of the single ions are there. I mentioned metal clusters. Metal clusters have to be done by hand currently because of issues relating to force fields. And there is at least one metal cluster that I have in a library. I've hinted at this already. So we're working on a library of amber restraints for all the ligands. And currently we have some hand-prepared force fields for different entities, including a couple of metal clusters, which were done by hand. The other entities in this library will be done automatically using Aldo and other Amber tools to create these force fields so that users have a better chance of getting to do a refinement because they will all be available in this library, but it's not complete. So yes to single metal ions, yes to some metal clusters, and I said it's difficult to produce metal-containing ligands. So these are things like heme. Now, it's difficult to create a force field library for heme on the fly for 2 reasons. One is that heme, everybody knows what it is, but nobody, you can't just optimize that using simple force field or simple quantum chemistry. It doesn't like to go perfectly flat. And the second thing is that the metal ion is often coordinated with the protein. So that coordination changes the force field parameters of both the metal in the ligand, like a heme, and the side chains, like the disulfide, like the cysteines or the histidines that are coordinating. So that just can't be done automatically. It's a limitation if the metal is in a ligand like that, not if the metal is a single ion by itself. Hope that answers the question.
Jonathan said thank you, so I think you answered his question. As you were answering that, I had a question. So the metal clusters you mentioned if somebody is using a tantalum bromide cluster for phasing, is that something that's going to be a problem for using Amber tools?
Yes. However, I mean, we're in this stage of trying to create a library. So if somebody says to me, we are trying to do this and we have this metal cluster, we can try and produce that and get it into the library so that they can use it. Or I can supply it separately. I mean, I should always point out that Phenix is very, very happy to help users, so they should contact us. I should have put a slide up. Just contact me directly if necessary, and we can help you try and get the force fields that you need. If this cluster is important to your work, we can try and prioritize that, produce it for you, and get it to you, in hopefully a meaningful time frame. It just depends on the situation.
Yep, you folks have a good reputation for being very responsive, and yeah, everybody has more things to get done than time to do them in, and prioritization is always a thing. So
yeah.
All right. There are no more questions in chat, and I haven't heard anybody else popping up. So once again, Nigel, thank you for presenting about this stuff. I thought it was interesting, and from the questions, the other folks did too. So thank you.
Thank you. Bye, everybody.